Hello, welcome to the stream. Hope you're having a good weekend. It's kind of warm today in Kansas City. I say kind of warm. It's high humidity, high temperature. We're in the midst of summer, so it's going to be a bit warm here in my home office today. But I'm excited to get started on the next chapter. So we are going to start chapter 5. And chapter 5, we before we had basically what amounted to a pure functional language. I say pure in the sense that we didn't have mutability. Maybe we should say we had an immutable functional language. I say it's not pure because we had side effects like read an integer from the console. From standard input, so that was not pure, but now we're going way into the impure, and I think the lesson here is that lots of languages have things like loops. They have mutable variables, and so it's a good thing to learn how to do. And Racket, as an example, which is a lot of the examples in here are based on Racket, they have mutable variables, and they have built-in functions or keywords, depending on how you look at it, that let you mutate those. But the main focus of today's stream is going to be getting started on loops. And they introduce mutable variables in this context because sometimes you want, well, not sometimes, basically all the time, you want to have a condition in a loop that will cause that loop to terminate. And the only way that you can have that is if you have an expression that can be evaluated where the inputs can change, right? So they use mutable variables as a way to indicate the termination condition. Now, if we were doing this in Gleam, or an Erlang, or an Elixir, where there is no mutability, you would do probably a tail call. What I mean by tail call is rather than having a construct with actually loops and has a condition, you have a function that you call that has a condition expression in it. And then whether that condition is, meets the criteria. I was going to say true or false, but it could be something else. If it meets the criteria, then you might do something and then call the same function again, and that's called a tail call. And the reason why it's called a tail call is because the last thing you do in that branch is you call the function that you're inside. Well, this language, we may get to tail calls, but they're not introducing that now. They're introducing loops. They're introducing, blocks of statements that don't evaluate to an expression, and mutable variables, so that we can accomplish loops. So let's have a look at chapter 5. Okay, so again, they're talking about imperative programming languages, loops and assignments to local variables. This is what we're focusing on. So here's an example. They're creating a value which will be the result of the whole program, using a let expression, and then they're introducing the loop variable I here, and then there's begin, and begin is a way to say these are a sequence of expressions that you need to evaluate. But I'm only going to care about the return value of the last one. We're just going to throw away any other expressions that may exist inside this. Now, the last expression inside this begin is the while loop. What does a while loop return? Well, you might say, oh, it returns the value of the last expression inside the loop, but does that make sense? And actually, I think that they define while loops to return void. They return no value, essentially. And then, so notice this begin has a while, right? right, and then the last value of this is sum. So I'm sorry, I was wrong. The while is not the only expression inside here. It's begin, while, and then sum. And so they're basically saying we're gonna, introduce a new variable sum, introduce a new variable I, and then after we've performed this while loop, the return value is going to be sum. So again, begin lets you introduce any number of expressions, which their results will be ignored. And then the last expression inside the begin will be the result of that expression. Okay, so let's look at the text here. So while loop consists of a condition right here and a body. The body is evaluated repeatedly so long as the condition remains true. So this is what you expect in a loop in most languages. The set built in consists of a variable and a right-hand expression. So here we have up here we've bound sum to 0 using a let expression, but inside that scope we are reassigning the value of sum to the addition of sum and I. Okay, and then we're also evaluating, we're reassigning the value of I to I minus 1. Okay, so the condition here is while I is greater than 0, I starts at 5, so we'll have 5 iterations of this loop. And so you're going to add 5, 4, 3, 2, 1, right? It's going to be the sum of those values is what's going to be put here. So we can know ahead of time what the result there is, but that's the sort of thing that you would do inside a while loop. You would have something that you want to produce that requires iteration, and then you would have a condition at which that loop should terminate. Okay, so the primary purpose of both the while loop and set is to cause side effects, so they do not give a meaningful result value. Instead, the result is the void value. So this void value is new. The expression void in parens is an explicit way to create the void value, and it has type void. So this is something we'll have to introduce to our compiler. The void value can be passed around just like any other values inside an L while. So we're extending elif with the while and begin and set. And it can be compared for equality with another void value. So if we have this this void value, you can say equal and pass two void values, and they are equal. However, there are no other operations specific to the void value in L while. In contrast, bracket defines the void question mark predicate that returns true when applied to void, and F false otherwise. Okay, so we're not going to introduce this predicate. Okay, with the addition of side effect producing features such as while loop and set, is helpful to include a language feature for sequencing side effects. Okay, so that's what they're talking about here. The begin expression consists of one or more sub-expressions that are evaluated left to right. So we have to have at least one, which is the tail, and then anything else that comes before it. And early on in this journey, we ran into a thing where read is a side effecting operation, right? So read an integer from the standard input. Order of evaluation matters there, and now we're introducing a construct which explicitly provides order of operations. So that'll be interesting. Okay, so here are the additions to the syntax, the concrete and the abstract. So I think that we might just go ahead and add those things. So we're going to create an L while language. We'll copy elif and add things to it. And I think we may go ahead and do the front end. So we did the parser and lexer in the last two sessions for the elif language. So we might go ahead and do that and extend it for L while. That'll be interesting. All right, so if you want to follow along, again, we've got the repository here, Sean Cribb's Essentials of Compilation, and we're working through it. So let's go back to our our repository here. Okay. So we're going to have to, we don't need that. We're going to have to add some keywords. And maybe this would be an opportunity. Maybe we'll do it next time. I kind of want to get as much into the meat of this as we can in the session, but maybe next time we could factor this out such that keywords are not necessarily keywords, but are just identifiers, and then we interpret them at a different layer, and that would simplify our tokenizer. But let's go ahead and add this. So we're going to need set bang, and begin, and while, and void. So those are new keywords. And then here, let's just dupe this a bunch. Okay, so we have, and I think that what we will need to do for set bang is do that greedy thing like we did with Lex. We did the EQ comparison. So let's plan to do that up here. Lex set bang. Okay, and that's going to error for now. But we need to add begin. This is keyword begin. And we have while. This is keyword while. And we have void. So I added too many here. Void. Keyword void. Okay, so let's duplicate this, and we may factor it out into a combinator at some point. So we're going to do set bang, oops, and then set bang. Okay. Okay, so there's an update to our Lexer, and then if we go down to our parser, we need to introduce, so set, begin, while, and void are expressions, and I think that what we're going to need to do is we're going to have to introduce our new language first. So let's do L while. And I'm going to copy all of elif. And we're going to have to adjust the type checker as well, because we are getting a new type, which is void. And let's see. Right. We don't have any new kinds of comparisons. Okay, no new primitive operations. Let's see. Actually, there's a question in my mind whether we call void a primitive operation. I think we might. And yeah, this is, we can't have the type and the primitive op have the same constructor. So we could call this void type or void t. Let me call this void. The other thing that we could call this is like make void or something like that. Okay, so so let's add the expressions now. So we're calling void a primitive operation. Okay. So we have while. Let's start with set bang. Set bang is going to be a var, is going to be a string, and then the value is going to be an expression. And then we have begin, which is going to be, I'm going to call it statements. That's probably bad. This is going to be a list of expression. But the goal there is to say that these don't result in any value being propagated out of them, as they don't evaluate to anything that is capturable outside the begin. And then I'll call this tail, or maybe we call it result, and that's going to be expression. Note here they go, it's, you know, expression star expression. So we're kind of mimicking that with list, which could be empty, and then the final expression, which is the result of the begin. Okay, and then there's while, and they're saying use while loop. I guess we'll call it that, while loop. Just be consistent with them. Okay, and then that has a condition, which is going to be an expression, and a body, which is going to be an expression. So you'll note in the text up here, for anything that requires more than one expression, thanks for the hearts. Anything that requires more than one expression, you get the begin. So this is how they're sequencing things inside the loop, while the loop basically only containing one expression in its body. Okay. Cool. So yeah, so we've defined all of those things. We're going to have to fix our interpreter potentially, or maybe we could just drop it. But they do go into in the first part of the chapter how to interpret things. Let's look at the type check. So here. We need to add the additional cases here. No. Yeah, it's not doing that. This is we're type checking individual expressions here, so we need to I want it to fill. Why is the LSP not working for me? Okay, so we're going to ignore the statements, and then the result, right? This is going to be here. We'll say statements because we're going to return this. Remember, our type checker here has the possibility of transforming things. We just haven't taken advantage of that yet. So here we're going to do use the thing. We need to type check all of these as well, but the result of our the result of our begin expression, it gives the type of the outer expression. So let's see. We're gonna have to type check the statements, and I need to think about how to do that because we've done this very like use style in here. I guess we might might have to do a list map. Does Gleam result have something like Rust's result does? Actually, just want the Gleam standard lib, where you can turn a list of results into a result of lists, right? Let's see. Okay, so let's look at list. The thing was, we can probably do fold. We could do fold until and return the first. The challenge here is that each of these statements, we only care that they individually type check. We don't need the result of that type check. We only need the left-hand side. Map fold. No. What is map to? Oh, that's map combine two lists. Okay. Transposes lists of lists. Yeah, I don't think that there's really a thing combining result and list in the same way that you can use collect in Rust over an iterator that returns that like the items in the iterator are a result type. Sorry, excuse me, I'm gonna take off my shoes. We could do, like I said, fold until, where we accumulate. Basically, we use the fold until to transform each of the individual results into OK and list of ASTs, or the first error. That seems reasonable, and what I wonder is what happens if if you run out of elements, I would imagine it would just return the accumulator. Let's see how it's implemented. Okay, yeah, so fold until takes a list and an accumulator and a function, and if the list is empty, it returns the accumulator. So if we get to the end of the list and there's no and there's nothing left, then it'll return that accumulator value. Otherwise, if there's an element and the remainder of the list, you call the function, and it has to return continue or stop. So I think what we'll do, forget the use for a second. We want to have we're going to use fold until. And it's going to take the statements. It's going to take an initial of OK and the empty list. And then our function is going to, it's going to be given the item, so we'll say statement, and the accumulator. Is that in that order? Yep. No, it's the accumulator first. This is going to be some not fun unwrapping. So we're going to type check expression. Oh, the other thing we need to do here. Whoops, I lost my place. We may need to no, we don't. I was going to say we may need to introduce the type environment to this, but everything inside the begin will either be, it'll be lexically scoped, so we're not going to introduce any new variables except let expressions. So we don't need to know the types of those things in the subsequent statement, right? There's no declare, declare X. There's only let expressions to declare variables. So you can, with our new semantics, you can set the variables that have already been declared, but you can't set something that hasn't been declared yet. So I don't think that we need to thread that through. So we'll type check the statement and the env. And here we need to say if it's okay. And the new statement and the type, which we will honestly just ignore. Then we need to look at what we want to return is continue. And we want to put inside this this expression. And the problem is it's going to be on the right. So I think we need to reverse. We'll untangle this in a bit. Okay, so now we're doing it right to left, which is, it's okay in this context because we're not, again, we're not introducing things that need to be tracked between statements inside the begin. Okay. So let's go back to result. think what we'll do here is result.map, right? Because we want to get the list that's inside this OK. And we're going to pass a function that's L, and we're just going to have it return S1. Is that how you do it? Too many dots? No. I guess the other thing that we could do is use one of these list functions and not... yeah, see, like, you're supposed to be able to do that. What's wrong with that? Oh, I have to give it the accumulator. That's the problem. Okay, and then, oops. And then if we get an error, then we do list.stop error E. Except it's error. Okay, so now it's complaining we're not getting the right returning the right thing. That's fine. So what we want to make sure here is that you know, the thing is we do need this. So so this expression is going to return a result. Statements too. And what we want is to return it's not R1 use and we're probably gonna have to introduce a use as well up here, because this is statements 2 is a result. Maybe we do use and we don't care about the type. Result.try statements. Okay, and this needs to be type check expression result with the env. And then here we're going to return begin. I'm sorry, this code is a little bit R1 TR. Okay, so let's see what's wrong here. Is it just complaining about not having inexhaustive patterns? Yeah, okay. So as long as it doesn't care about this here, we can just do error. Okay, what's wrong here? Expected type. Oh, and the other thing that here, list of expression. We need to do list.reverse to put it back. Oh no, we didn't, because we built it backwards. Yeah, so like either we need to fold over this in order and reverse it down here, or we reverse it before we iterate. It doesn't actually matter that much. Right, so this is exactly what we wanted for this. Is this should be a result, which is a list of expressions, and we can unwrap this into a use. So we could do use statements is result.try or list.fold until. And actually, that's not right. This is I'm not sure how to flatten that. Okay, so this is a result of a list of expressions. So result.try so the problem here is I was expecting a tuple and it's not a tuple. Okay. Right, so this is what's wrong here? Did you mean to wrap this in an okay? No, I didn't, because we have a use. We're not doing that up here, right? It's probably our combination of let and use here that's a problem. So what we could do, I wonder if we could pipe into the use. So we could say statements, start to pipe this, list.reverse, list.fold until, okay, and then give our function, and then pipe that into the use. Yeah, it doesn't like that. When you get into doing pipes and use, it gets a little bit janky. So let's do. I still don't know why it's not. It doesn't like the type on this. Did you mean to wrap this in an okay? No, because the previous thing is a use. Weird. All right, let's leave that for now, and I think we need to fill out the other we need to fill out the other expressions here. So I'm going to do, because we added the void op down here as a primitive operation, I'm going to say this is void and the void type. And this is just okay, right? It's similar to, well, it's not similar to anything in there. Okay. All right, let's look at our other. I need to get these side by side because I'm running out of space here. So we have, we need to do set bang. This can be var and value. Okay, so here, what we want to do is so we want to type check the expression not E and V, value, right? And then we need to have a, let's see, right, something like this, type check equal, check type equal. So in the case of set bang, we need to make sure that the variable in the environment, let's see if we look that up somewhere. Right, so we could delegate this to type check expression of the var. So we could do, we don't care about that, but we want to, we'll call it tval and tvar. Type check expression of var of that. E and V. So that's going to give us the type of this, and then we're going to do basically result.try type check type equal. And what does that take? So it takes a type, two types, and an expression. Okay, so we need to use this expression here. As the context. Okay, so we're going to say we want tval and tvar. We'll say tvar first because that's the thing that already exists, and then we're going to pass it and v1. That's the expression, and then finally we're going to return set bang var, and value is v1, and the type is always void. Let me comment this out and see what's going on here, because I think that I got something wrong with the nesting here. Let's ignore that. Does not have a pattern for all possible values. Okay, well let's put in the underscore here. This needs to be a type error. We had a type error. I'm gonna make this bogus. That's not correct, but okay. So this is gonna need to contain. Oh, this is void type. Okay, so that's our problem here. We have the value void and we have the type of the value void, and it's still complaining that this, but we never had to wrap any of these. What's the deal, yo? I need to put this case in up here so it doesn't. Keep bugging me. Void type. Okay, because this should, with the result.try, oh, this last one needs to be a result map. That's the problem. Because you want to return a result. Like the tries, you do everything up until the penultimate one, and then you use map. So that was the problem that we were having up here as well. Okay, and I just need to fix that. Okay. Whew. So I remembered me some Gleam. All right, so we also have, so we did set bang, we did begin, and we have while loop. And we have the condition and the body. Okay, so we need to check, first of all, that the condition type checks. And then we need to check that, excuse me, check type equal, Boolean, of so TC, and the expression is C1. Okay, so that condition needs to be a Boolean, and then I wonder whether it matters what the value of the while loop is. I think we can just ignore it as long as the thing's inside it type check. So we're gonna do and if that type checks, then we're gonna return while loop of condition is C1 and body is B1, and then the void type. Okay, and that I think covers everything because it's saying, yeah, you can't reach that. So we've covered those. We covered the operations. And I'm tempted, so we have a lot to do in the interpreter. I'm tempted to rename all of these to like t integer or integer t, and this to void t. Yeah, let's go ahead and rename those symbols. Oh, please don't mess it up. Rename symbol void t. That did not work. Okay. We're going to have to do find and replace. So everywhere where it says integer, we're going to say integer t. Let's go to the next one. Those are just panics. Replace that, and that, and that, and that, and that, and so forth. Okay. Let's change Boolean to Boolean t. This is just to distinguish the type from any value or expression. So let's go to the first one. Okay. Yeah, we need to make sure that, let's match whole words. Let's use match case sensitivity. Make sure that there's no strings, and then I'll just do replace all. Yeah, looks right. Okay. And void type, let's change it to void t. Replace all. Okay. All right. So I've renamed those. So we won't have any conflicts there, and like it'll be clearer, right? Okay. So now we need to handle interpreting. And I think that the simple case here is, so this is a primitive operation. We're going to need an interpreter value called void value. Of course, that's a singleton. You can't have anything inside it. And so interpret op here. We need to make a case for void, and honestly it's just going to return void value. That doesn't really do anything interesting. So up here it's going to be interesting making sure that we sequence things correctly. Okay, so maybe we should do the easy ones. So set bang, which has a var and a value. Since this is imperative, our interpret expression is going to have to return an E and B. So we're going to have an I value and an E and B as the return, which means that on all these things, we need to return, right? And interpret op, these don't have any side effects. The primitive operations. in the sense that they would change a variable value. So we can just assume that they will return the same E and B. And the same thing here. And the same thing in let. And actually that's not right. Well, no, it is right, because for let, the variables defined by let do not escape. So we do need to call interpret expression. I suppose you could have something with, like, inside a let binding, do a begin that modifies a variable that's already in scope. So yeah, we need that. Okay, and then here it would be, you would interpret the expression with the newly assigned thing. But if this, yeah, if this modifies anything inside, yeah, I don't see how we get around. Right, we'll get to the patterns here. Let's just put a to-do on that. And then here, so bool value, oops. And env, that has no side effects. Again, like, I don't see any reason why a condition couldn't have a begin inside it. It's crazy, but we have to consider that. Because this is imperative, right? Like, side effects matter. Okay, so now that we've got set bang, what we can do is we can evaluate the value. And then what we do is we will return void value, and we will insert into env1 for var the result. So we have side effects inside side effects, potentially. Not fun. But it's okay. So the potential thing that could get interesting here is the while loop. Let's handle begin first. because I think that's going to be the most straightforward to handle. Okay. So we need to do, again, we're throwing out the result of each of these expressions in statements, but what we need to do is thread through the env. So let's do, we're going to do a list fold. Let's see. Yeah, and this is going to be overstatements. And we're just going to have void value here. No, we're going to start with the original env, right? And then this takes the accumulator and the statement, and is going to do, we're going to ignore the result of it and do interpret expression of statement and the accumulator, and then we're returning env1. Right, so since this expression could have a side effect, we need to walk through these in order. And then finally, what we will do is we will just interpret the final expression of result with the env1. So again, we're only evaluating those for their side effects, and then the last expression in the begin is the return value of that expression. Okay, so now while. I have a feeling that what we need to do is basically have almost an unbounded iterator, and I would love to just recursively call interpret expression, and maybe that's what we do. Yeah, I bet we could do that. So what if we do, we're going to interpret expression on the condition with the env, right? And if it returns false, then what we return, except the thing is it's going to return and, some value and a new env. What we return is void value, right? And the updated environment, because again, conditions, they don't have to be side effect free. Okay, if it returns a bool value of true, then we need to execute the body again. So what we will do is we will here, for anything else, we're going to have to panic invalid Boolean expression, right? Because it didn't evaluate to a Boolean, the condition. I love it when I miss. It pops up the emojis. My code needs more emojis, don't you think? Okay, so if it evaluates to true, then we need to evaluate the body again. And so what we will do is we will forget the result, and we're going to interpret expression on the body inside the updated environment. And then we're going to call interpret expression again with the same while loop and the updated environment. Okay, so I'm introducing tail calls here, right? Right, so if the condition evaluates to false, we just return void because while has no value returned from it. It's only used for side effects. And then we return the updated environment. If it returns true, that means we need to evaluate the body of the while loop again. So we go and evaluate that, and we call ourselves. So we tail call to here. We're still evaluating this expression, and I've forgotten the Gleam. Is it like expert? Is it like expert at? How do we do that? Is it like that? I've forgotten. Anyway, so we don't have to do a kind of, like I was thinking about things like we did previously in Unfold, which is like you have a generator, and that generator will emit items until it completes. Yeah. Okay, so we need to, it looks like we need to adjust this. Look at all these failing, because they're recursively calling interpret expression. And so we need to adjust interpret op. Where are we calling that? Right, so we need to make interpret op return the env that it modifies. Because these expressions in here can, like this, this is why actually functional languages are way easier. Like you think, it's hard to think in functional languages, but actually side effects are the devil, right? They are so hard. Okay. So what we'll do here is we're going to have to modify all these so that they handle side effects. And here, these have to be sequenced, right? So left to right evaluation, which means in our interpreter, we have to thread the environment through each of the expressions, left to right. basically doing the same transformation on all of these. And my typos are getting tedious. I'm very sorry. Okay, we're getting close to it. Interestingly, if you notice here, we have I'm going to change these to non-Boolean because you could throw void in there, and that would not be good. Oh, and here we need to make sure to use E1 there. Okay. Okay, so here we're going to have to change this to make it look more like this. So let's unnest this and say let assert we need to handle void as well here. Let's call this a value E1 is interpret expression A, E, and B, and then we have let assert B value E1, and we maybe don't need the assert here. Right? Because we're not trying to assert the type yet. And this is E2, right? And then we'll do case honestly, I think that what we do is yeah, okay, so we're going to do case AVBV, and we'll say int value BI, and then we'll say we'll return bool value AI equals BI and E2, right? Because we need to return the environment. And then we'll do bool value AB BB, and then if we have void we just returned bool value true, right? And E2. So this is what they were talking about, where you can compare two void values with EQ. And then anything else will panic as mismatched types in EQ expression. Okay, and then we can get rid of this. Okay, and then we just have oh, this is void value. Thank you. Okay, and then finally down here, we need to thread through the environment. So E1, left to right. And then here we return E2 on all of these. Actually, let's just wrap the thing, the whole expression. Okay, so then here for void, you know, the void primitive op, we just return void and unmodified environment. Okay, I think that covers everything. Wow, that was a wild ride. I hope you're still with me. So, let's look at the errors. What are we doing here? Okay, so we have a little bug there that I just fixed. Because if we evaluate that expression and it modifies the environment, then we need to pass it through. And then what else is wrong? Okay, so I have a bug here where I typed bool int value and I need to say bool value. Okay. Love it when the compiler gives me useful errors. Okay, so now we have a full interpreter, and I think that what we should do is make a little test for the interpreter. So we haven't done one in a while. And then what we'll do is we'll hook up our parser to while instead of elif. And then we'll have, you know, top to bottom. And actually, let's go ahead and do this. What I think I want to do here is, because I think that what we were doing was we were going into the language, so the AST definition and the interpreter, and we kind of got off on that tangent of the interpreter and the type checker. But what we were originally wanting to do is be able to construct stuff from the while language. So I think, yeah, I'm going to say as lang, so this will be easier to change later. And let's find all the places where we say elif dot and replace them with lang dot. Okay, so now I can just swap this like a while. Okay, and then down here, set bang, the lexer needs to handle, this is not comp, but set bang, right? Okay. So that handles our lexer. And if we get down here to the parser, we need to right, so we need to have, we need to introduce these things here. So primitive, we need to make a void op here. And I'm going to put it up at the top. Token keyword void. Right? Okay. So that handles our new primitive operation, void, constructing the void value. So I think the answer is in here. We have if expressions, let expressions, and primitives. So this is where we need to add our set, bang, begin, and while. So honestly, probably doesn't matter which one. So we're going to have a begin expression. We'll have a while expression, and we'll have a set expression. Okay, so begin expression is a parser, and it returns a language.expression token nil. Okay. So for this, and remember the reason why we have nested is that we want to match the parens separately from the contents of the parens. And this is sort of a like thing where it coalesces the look ahead needed to determine the kind of expression into this parser. So like if you, it prevents the need for backtracking basically. So if you match a paren, then it's got to be one of these things inside of it, and then you need to match a closing paren. Okay. So for begin, what we want is a token, which is keyword begin. And then we want to get the statements. So we're going to have to look at nibble. I think I still have the, yeah, still got the docs up here. So we have many, which is any number. So we'll do use statements. Do nibble.many. And I think we need to do many one. And what we'll do is we'll take the last off of there, because we need at least one expression. Right, so we need to do expression. So that's a list of expressions if it parses. Sorry, that's not caps. Nibble.token. Okay, so then we need to take the last of the list. And I'm wondering if we need to do a multiple list reverse thing here to get that. Yeah, I don't need that. Okay. Well, let's look at the Gleam standard library. Okay, so this is a parser. Do returns a parser. I honestly think we just do let assert. The other thing is that we could do is we could split. Right, so if you split at so length, it'll give you, so we do length minus 1. Okay, so we'll say this is we'll call this expression. So we're going to say this is statements result Okay, I actually think that I'm going to do we'll do let assert result statements, and we'll do list dot reverse. We'll just let it panic there. And then what we're going to do is we're going to return do the trick of reverse and then reverse again. It's not great, but here we are. Result. Okay. So now we need a while expression. Okay, so we're going to do use, and we're going to, this will match on the token of the keyword while. And then we have a condition. Yep. We have a condition, and then we have a body. And then we return while loop condition body. Cool. That worked out nicely. And then finally, a set expression is going to be, again, the same parser. So we have the set bang keyword. And then we need, the var is going to be an identifier, right? And let's see. Right, so that returns a string. Okay. And then we have another expression. And then we return lang dot setBang var value. Cool. Okay, so now we have our AST, we have an interpreter, type checker, and we have updated our parser to use this new language. So what I want to do down here, we're going to import EOC langs l-while as lang. Well, let's import it as l. C langs parser, or passes parse, yeah. And we're going to take advantage of the bit we did here. And now this test is going to fail because we have switched it to use this. So we're going to change that to l-while. Okay. Okay, and let's make because let me change the parser. Parse while test. Let's use their example from the book. So if I can select all of it, there we go. Okay, and there's a question here whether I should maybe, yeah, let's go ahead and construct the program. But here, let me put this is should be okay. Parse should be okay. And then should equal p. Okay, so we're going to make a program. Okay, and why is it not complaining about that? What other bug do we have? All right, so we need to change that here. That's not an issue necessarily, but and then we've got issues with all this. So we're gonna have to update all of those, but that's fine. Now what? Yeah, it's complete fine. I don't care about those. What's going wrong here? Okay, so we need to construct this program. We're gonna make let, and let takes a string, let sum 0, and then we're gonna have another let inside there. Just take I 5, and inside there we have a begin, which is, and actually I need to indent this correctly because that's lined up with that. Yeah, the while and the sum are at the same level. So this is going to be sum. So we want to return sum at the end of that begin. And then in here we'll have while loop, and that's going to have a comparison of greater than a variable I 0, and that needs to be wrapped in a prim because it's a primitive operation, right, to make it an expression. Okay, and then the while loop is going to contain a begin, and it's just going to have one thing in the list, and the ultimate one is going to be set bang I, and this is going to be primitive operation minus I and 1, and then we'll have another set bang sum and a primitive operation of plus sum and I. Okay, so let's run. Let's see about. We'll make a test in here in a minute. Yeah, let's leave it just to do. Yeah. Okay. So. So we've messed up some stuff with our parser. So let's look at the parse test. So the tokens test. If line 1, column 25 is, yeah, no match found if. Interesting. Okay, so the parse test. Where is that? Yeah, so we messed something up in our tokenizer such that this one doesn't work. And it's happening at if. Okay. So I wonder, well, I don't want to spend too much time on the Lexarm parser side. I wonder whether I should pull in the stuff for dealing with this issue of greediness that we ran into last time, and basically implement Racket's rules for identifiers. So I don't know if I still have that up in my browser here, but yeah. So here in the Racket manual, identifiers is basically saying excluding these special characters, and except for the sequence of characters that make number constants. So you can have numbers in the identifier, but it can't start the identifier. So almost any sequence of non-white space characters forms an identifier. For example, substring is an identifier. And string append and a plus b are identifiers as opposed to arithmetic expressions. So interesting, like that primitive operation is an identifier. So what I think we need to do is in the Lexer, we're going to combine, let's see, basically we're going to use this as the negative set, right? And then we will pattern match on any of these special values for the identifier. And where we know it's one of our built-ins, essentially, it's either a comparison operator or one of the other primitive operators or some other keyword that refers to something that we implement in the language semantics and not as a function. Then we'll return the keyword. And we'll get rid of this using this built-in Luxor. And I'm hoping we can do that in 20 minutes. Okay, so let's do... we'll leave these tokens in, and basically everything down to... and actually this is fine. Let's do the integer up here. So all of these we're going to combine, with the exception of the white space, we're going to combine them into a single Luxor, which is read anything that's not one of these special characters, any number more than one, and yeah, and it'll actually be similar to this Luxor.variable, except we're going to do it slightly differently. So here, let's go to definition on this, and I want to see where is... So variable does identifier. If we go to identifier, right, so what we will do is we'll take this to value. We're going to do something similar to what identifier does. The thing is, we don't care about reserved words. We're going to interpret the reserved words. So I guess what we could do is use this and just have an empty reserved word set, and then we'll handle the keywords, so to speak, in the toValue function. Okay, so we're going to say Luxor.identifier. Let's try identifier. Yeah, we don't need to use that. Okay. So this takes the start set as a regular expression, and we're going to use the negative capture group. So parens, and we need to escape the brackets, and we need to escape the quote there. Okay, so it has to start with anything that's not that, and we also need to make sure that it starts with anything that's not a number, because if it starts with a number, it should be an integer constant. And then after that, we can have basically anything that's not one of these reserved symbols. Okay? The other thing that we need to do is make sure that there's no white space in there. So also including white space. Anything that's not one of these symbols or white space. Okay? And then we're going to return a set new. We're going to be an empty set. Yep, we already have set in here. So we'll give an empty set of keywords. And then we're going to take a function that gives the token, or gives the text, and we'll say case text, and then we're going to so I think we actually need to keep this one in here. These two start with reserved symbols, so they need to be in there. Because this, it can't start with bang, or it can't start with the hash mark. All right, so now we can do like, is it plus? Then we're going to map it to keyword plus, and so forth. So let's move all these up here inside the case. Oops. Everything but that Lexer ignore. Okay. That's keyword plus. And we'll have minus is keyword minus. And here we'll just make use of the direct pattern matching that Gleam offers to sequence these things. And I wish these were aligned in a column that I could just easily do this. So here, if it's anything else, then we want to return identifier. This is going to be the base case, right? And we can get rid of this, and yeah. Okay, so let's move this down to the bottom of the case, and then we'll handle all these as quickly as we can. Note here that I am putting the greater than equal and the less than equal first. It's probably not strictly necessary because these will be, terminated already. Okay, and then we have EQ. This comp line.eq. And then we have set bang is going to be keyword set bang. Okay, handle those. And these are all keywords. Let's see if I can line these up so that it's easier to edit really quickly. Okay. So let's bulk edit this. And then we're going to go from here and replace that with arrow. We're going to go to the end and backspace, backspace. Okay, so that's actually, and we can get rid of all of that, right? We don't care about the reserved words anymore. That's actually easier to understand, except for this crazy regular expression. And then we can get rid of these special greedy lexers and use this simple one. Okay. Boy, I hope that regular expression works. I guess we'll find out. So let's run the test again. Okay, so we got issues. So it's clocking this as an identifier. I think that's the fix there. Okay, we got different ones. So we're getting the keywords here. Okay, but we're getting identifier if. Did I not put if in here? I don't have if in here, so that's one of the problems. Somehow I lost if in that transformation. Honestly, doesn't matter where we put it. Okay. Let's see what we got. Okay, we're getting identifiers for white space. So I wonder if we move this up. I don't know that it needs to be. Yeah, and I think we need, like, I was hoping to use just the S character class. So looking at this, like backslash is a special character. That's why we have the backslash here. So I think I need like that. Not really great to put in there like that, but let's see if that. Okay, so that fixes it, except for our to-do. That is great. That means that this is working, covering the cases that we already were doing last time. Okay, so now if we go to our a while test, we can. Oh yeah, that means our parse test with our new. That's equal. So we actually passed that one, which is great. Our only failure was the test that we'd stubbed out. Okay. So what I want to do is I want to take this program and we'll put it over here. And we're going to parse.tokens. Should be okay. Okay. Okay, so this should return us a program. And let's say that's our program. And then what I want to do is I want to say we're going to type check. We're going to type check program. And that's going to return a result. Oh. What happened there? Should be okay is what we want to say there. All right, so I just want to make sure it type checks. And then let's do our evaluation. And I think that what I can do here is chain these, because remember that type check returns a potentially modified program. We're not using that in the type checking yet. But then we should go interpret. And we can say what it should equal. So knowing this program, and we know this starts from 5 and counts down. So we're adding 5 to 4 is 9, 3, 12, 2, 14, 1, 15, right? So it should equal L.int value 15. All right, let's run that test. See if our interpreter is correct. Our interpreter is correct. Woohoo! Okay. So this is a pretty good place to stop. We've got the front end. And next time, we'll get deeper into the different phases. So one thing that's great about this is that we know, based on all of this, that we got our order of operations correct. We're pretty confident with that. We've type checked the whole thing. And yeah, so look, by the way, you know, I was talking about tail recursion earlier with Gleam. What they're doing here is in Racket, they're defining a local function, and it defines a function loop, and it uses recur. Yeah, that's some crazy Lispness that I don't know. But the other thing is, they mentioned in the text here, they box and unbox, and I think that's so that their loops use the most current value. Yeah, interesting. But we don't need to worry about that because that's not part of the semantics of Gleam in our interpreter. Okay, so let's look quickly at the type checker for, yeah, so they add begin, set bang, while loop, and begin. Yeah, so okay. So what we'll do next time is we'll get started talking about cyclic control flow and data flow analysis, and that'll be some really interesting stuff and potentially challenging. So please join me next time. Thank you for sitting through this. I'll make a really quick commit. And this is chapter 5. So we're going to say this is AST type checking and interpretation for loops. Good stuff. And we'll push that. Let's look at what the okay, it's complaining about that. Why do we care? Let's close look. It's complaining about interesting, we're not using string anymore. Let's fix that real quick. We don't care about the warnings in there. Yeah. All right. Well, thank you so much. See you next week. Take care.